All right, let's dive into a paper that really shook up the world of computer vision, DINO. We're going to break down how this end-to-end object detector pushed transformer-based models to a whole new level of performance.
Okay, so let's just jump right to the headline result, the thing that made everyone sit up and take notice. What you're looking at here is a plot of average precision, the key accuracy metric, against training epochs. And that pink star, that's DINO. It's not just that it's way up there at the top, it's how fast it gets there. This was a huge deal, a new benchmark for both speed and accuracy.
And the paper's abstract says it all, really. DINO didn't just inch ahead, it set the new state-of-the-art on COCO. And think about what that means. It beat everything, even the super-tuned classical detectors that relied on all sorts of handcrafted components. We'll get into why that's so important in a bit. So here's how we're going to break it all down. First, we'll look at the context around DETR. Then we'll dig into the three big innovations that make DINO special. After that, we'll check out the results, and finally, talk about why this model was such a landmark. Okay, so first up, the DTR context. Before DINO came along and changed the game, DTR-like models were promising, for sure, but they were also running into some pretty serious walls. So what were those walls? Well, for starters, they were just slow to train, which is a huge pain for research and development. And the big one? Their performance just wasn't quite on par with the best classical detectors out there. On top of that, there were open questions about what the queries were even learning and whether this whole approach could really scale up with bigger backbones and massive datasets. Right, so that was the problem space. Now for the fun part, the solution. DINO introduced three core technical innovations that tackled these issues head-on. Let's get into them one by one. First up is something called contrastive denoising, or CDN. Now, this builds on an existing idea of denoising, but with a really clever twist. It's not just about teaching the model to fix a slightly noisy or jiggled ground truth box. The contrastive part teaches it to tell the difference between a good starting point and a bad one. And this visual explains it perfectly. So, you've got your ground truth box in the middle. The model gets fed positive samples. These are basically the GT box with a little bit of noise added, all inside that inner square. For those, the goal is, hey, reconstruct the original box. But here's the magic. It also gets fed hard negatives, these boxes in the outer ring. For those, it's trained to say nope, there's no object here. This is how it learns to reject anchors that are close but not close enough. So why does this matter? Well, it directly tackles the problem of duplicate predictions. When you get multiple boxes for the same object, this helps clean that up. And as we'll see in the results, it gives a massive boost to performance on small objects, which has always been a real weak spot for these kinds of detectors. Okay, innovation number 2, mixed query selection. This is all about how you give the model its initial guesses, or queries, to start looking for objects. It's a smarter way to kick off the whole detection process. And this diagram shows the really clever part. The model looks at the encoder features to get hints about where to look. These are the positional priors. But, and this is the key insight, it keeps the what it's looking for, the content queries, totally separate and learnable. This stops the model from getting confused by ambiguous features early in the process. Basically, you get the best of both worlds. The decoder gets really good hints about where to look, but it doesn't get biased on what it should find there. By separating position and content, the model can then go and pull much better, more comprehensive features from that location. And that brings us to the third big idea, a really neat training scheme they call look forward twice. This is all about improving how the bounding boxes get refined layer by layer in the decoder. So check this out. Normally, a decoder layer learns from its own loss. But with look forward twice, a layer, let's call it layer I, also gets gradients from the next layer, I+1. It's like the earlier layer gets a peek into the future to see the more refined box from the next step and uses that information to get better itself. It's a really clever way to propagate knowledge backward during training. And the upshot of all this, it helps optimize not just the refinement offset, but the initial box prediction as well. It creates this much tighter feedback loop across the decoder, which, you guessed it, leads to more accurate final bounding boxes. All right, so we've covered the three core ideas: contrastive denoising, mixed query selection, and look forward twice. Now, let's see the proof. How does this all stack up in practice? And the results are, well, they're pretty staggering. Just on a standard ResNet 50, with only 12 epochs of training, DINO hits 49.4 AP. That is a 6-point jump over its predecessor. And look at that score for small objects, a 7.5 AP gain. That tells you that contrastive denoising trick is absolutely working. Remember that slow convergence problem we talked about? Well, this graph is the solution. That red line for DINO just shoots up and settles at a much higher AP. It's not just better, it's faster, way faster. This was a total game changer for training efficiency. And what happens when you scale it up? It gets even more impressive. This table compares it to the other heavy hitters on the COCO test dev set. DINO hits the top spot, 63.3 AP. But look at the model size in pre-training data. It's a fraction of what its competitors were using. It's doing more with so much less.
And that's the number that really matters, 63.3 AP. This wasn't just another small step forward. This was a fully end-to-end model, no funny business, setting the new record on the most competitive benchmark out there.
So when you put these two charts together, the story becomes crystal clear. On the one hand, it's way more efficient to train. On the other, it achieves better performance with a smaller model. It wins on speed and it wins on power. It's the whole package.
So let's wrap this up. What's the big takeaway? Why do we still talk about DINO?
DINO's legacy isn't just about that top score. It's that it was the first purely end-to-end detector to get there. It didn't need any of the old handcrafted parts like non-maximum suppression to clean up its predictions. It proved, once and for all, that the whole DETR philosophy wasn't just a cool academic idea. It was actually the superior way to do object detection. And that leaves us with a really big question for the whole field. If DINO can be the best in the world without things like non-maximum suppression, do we even need them anymore? It really forces you to ask if the era of these handcrafted components is finally over, maybe even faster than we thought.